Okay, good morning, everyone. My name is Josh. I'm a software engineer. I work for Oracle and I'm a member of the database group. So specifically, I work on projects related to XML and JSON processing in Oracle database. So today I'm going to be talking about JSON and Oracle database. And most of my presentation is going to be pretty technical. It'll include several live demonstrations. I'm going to get into the details of how we process JSON and how that data can be accessed efficiently. I'll show how an existing MongoDB app can be made to run against Oracle database without having to make any application code changes. But before I get into all of these details, I'm going to start by talking for a few minutes about document storage in general and why you might want to model your data as JSON. I'll talk about the database landscape, and it'll be, kind of high level. So if you're a developer watching this and you think at the beginning, oh, this is too high level for me, please bear with me for the first 10 slides, and then we'll get more detailed as we go. So a document store is a type of NoSQL database. In fact, it's the most popular type of NoSQL database. And one very notable example in this category is MongoDB. So these databases in this category store JSON or something like it. JSON's this really simple format. It has a small set of types, basically strings, numbers, booleans, objects, and arrays. And these types can nest within each other. So an object can contain an array of other objects, for example. And the other kind of notable characteristic here is that it's self-contained. So what this means is you don't need a separate schema defined somewhere in order to read the data. So the example on this slide contains a JSON object representing a movie, the movie Iron Man. It has attributes like the title, date, cast, and so on of this movie. So my group at Oracle isn't building one of these document stores. Our general strategy at Oracle is that we're building a converged database. We're building a single database that can handle multiple types of data and multiple different workloads over that data. This strategy is very different from some of our competitors, notably Amazon Web Services. Amazon suggests that you should use multiple special purpose databases depending on the use case. So like if you go to Amazon's marketing page on databases, they basically have messaging that sounds sort of like you should use the right tool for the right job. And this messaging can sound good and make sense, but we believe the reality is that it will lead to systems that are expensive and inefficient. So following their approach, you're going to have multiple licenses, multiple security models, multiple skill sets to maintain, ETL processes, all of this stuff just becomes very complex. So to that end, over the past 15 years or so, we've been putting a lot of functionality into the core kernel code of Oracle Database to make it really good at solving these NoSQL JSON-like use cases. And the other thing about these special purpose databases is that they tend to come and go, or a lot of them do. When I joined Oracle around 2008, our group was focused on XML. And one of our biggest competitors at the time was this database called MarkLogic. Everyone was talking about, like, how are we going to compete with MarkLogic? How are we going to beat MarkLogic? And now, like a decade or so later, we never hear about them anymore. And, a year or so ago, they were bought by another companies, which might not be a good sign. This has also happened with Hadoop to some extent. So Apache Hadoop is this big data processing ecosystem, and it seemed like it was going to take over the world. So at some point, our group became engaged in several projects related to XML and JSON processing in HDFS, MapReduce, and Hive. But now, again, 5 to 10 years later, it seemed like a really big deal, but now all the activity on these projects has faded and nobody's talking about it anymore. So many of these special purpose databases can seem like a very big deal at the time, but they become marginalized later on. And on the other hand, there's a group of relational multi-model databases that started out relational, like Oracle. And these databases continue to be very popular today. So dbengines.com is a website that scores databases based on their popularity. They do this by like tracking how often a database occurs in search engines, how often it's posted about on Stack Overflow, LinkedIn, Twitter, and so on. They combine all this information and somehow come up with this numeric score for each database. You know, the larger the score, the more popular the database is. I don't know how this algorithm works exactly. I think something like this you kind of have to take with a grain of salt. Who knows how they actually compute this number? But for whatever it's worth, 7 out of the 10 most popular databases, according to this metric, are relational databases. These databases have been popular for many years, and they continue to be popular. But there's one interesting thing here. More recently, in the past few years, MongoDB has made it into the top 10. It's the only database in the top 5 that isn't one of these multi-model relational databases. So they're ranking hundreds of databases here. So for MongoDB to make it in the top 5 is not insignificant. So there must be something that people like about it. One reason that they like it is that storing data as JSON is schema flexible. There isn't, for example, some static table with fixed rows and columns holding the data. So if you want to just store your application data, you can often do so without a lot of effort. Then your data can continue to evolve and you can store new data over time. Like for example, if you decide you want your web app to store some new field, some new piece of data, you can do this without, for example, having to ask a DBA to modify some backend table definition. It puts the control of the schema in the hands of developers. It maps well to application objects. It supports these nested repeating objects. It allows you to store your data in the same way that it looks when it's in your application. You're not having to join multiple flat rows together in order to materialize this, application object. And then finally, well, SQL is really great for analytics. It's sometimes a barrier to entry for engineers that just want to do simple persistence. So like MongoDB will say things like data as code. You're just kind of more programmatically working with your data. You don't have to write any SQL. And a lot of developers find that appealing. The other aspect to these NoSQL document stores is that there's kind of a performance aspect. Databases in this category are thought to be scalable or elastic, meaning you can increase the compute and storage capacity as demand, for your data on your database grows. They're also typically used for building, interactive applications. So response time is very important. So lots of these databases advertise that they can maintain single-digit latency at scale. And what they mean by that is that even when a lot of people are accessing the database at once, they can keep the response time for small reads and writes under 10 milliseconds. Also, these NoSQL databases are perceived as being highly available and low cost. So there's kind of this performance, scalability aspect, and then there's this data model aspect. And that's kind of the salient characteristics of these databases. And so our group at Oracle is that we are making Oracle database solve the same use cases as these NoSQL document stores without losing or giving up the traditional strengths of Oracle database. So I'm going to be showing you how you can write these schema flexible, low latency, high throughput interactive applications over Oracle database. And you can do this without losing the ability to do things like consistent reads, durable writes, and have SQL evaluation directly over your data. So that's about the end of my introduction. But this last slide here, before I get into the technical details of how this all works, I just want to mention the autonomous database. So the autonomous database is really Oracle database, but it's the managed version of Oracle database that runs in the cloud. Managed here means that you just get access to the database. We take care of things like installation, patching, scaling. People really like the autonomous database because it has the best of all, the features that we have to offer. And at the same time, it has a low total cost of ownership because you don't have to manage it or scale it or worry about performance. Like that's kind of taken care of for you. You just focus on, building the app. So I'm going to start doing demonstrations shortly, and in the demo, I'll be using the autonomous database. But I also want to say that all of the stuff that I'm about to show you it's all available with the standard normal license of Oracle database. So if you're listening to this and you already have an Oracle database license, you're already, paying for all of the features that I'm about to show you. And so with that, let's get started. So the next section is about how we've basically changed SQL to accommodate JSON storage. So when you hear relational model, typically you might think of the following. You've got a schema or a database that has a bunch of tables. Each table contains rows. These rows have columns with simple values. They don't have nested structures. These rows have a very rigid structure, meaning that each row has exactly the same columns. And the only way to access these tables is using SQL. So the example on the slide shows a table containing 2 movies. It has the attributes ID, title, and date. And then if you wanted to access this data, you might write a select query in SQL that looks like this, where it's selecting the title and the date of these movies for one where the ID is equal to 1, 2, 3. So that's kind of like the canonical or traditional relational model. So how did we bring JSON into this? Well, the first thing we did is that we created a JSON column type. It's a very simple idea. You create your table, you have a column of type JSON, and then you can insert JSON inside of that column. The example on the right here creates a table called movies, and it has a column named data of type JSON, and then it's inserting a movie object, a JSON object, inside of that column value. And then the other thing we've been doing is working as part of the ISO SQL standard to define extensions to SQL for processing data in these JSON columns. The basic idea here is that anything you can do with a row, a normal row in SQL, you can also do with one of these nested JSON objects. So you can do projections, joins, you can map JSON objects to relational rows, you can map rows back to JSON objects, you can do aggregations, analytics. Basically, anything you're used to doing with relational data, you can also do with these nested JSON objects. And we've been doing this kind of thing since 2013 with the release 12c. But things have been getting interesting more recently. In versions 19, 21, 23, we've started to store JSON in this binary encoded format we call OSON, instead of just storing it as plain old JSON text. And it's not just Oracle database where this is happening. So that slide I showed with the top 10 database, a few slides back, all of them now support some form of a binary encoding for JSON. Even SQLite, this lightweight little database, announced months ago that it now also has its own binary encoding for JSON. And so the next couple of slides talk about this binary JSON format and why we, in particular, have moved away from JSON text storage into this OSON binary encoding. So the first reason we did is we wanted more types, right? So JSON has a fairly simple set of types: objects, array, string, true, false, null, and number. But we wanted more. So we added floating point numbers, timestamps, and intervals. And the reason we wanted more is for two reasons, right? We wanted the ability to go back and forth between table rows and JSON objects without losing information. For example, this table here has a timestamp column, and we can convert that to a JSON object without having to convert that timestamp to a string. And the other reason we wanted these extra types is compatibility with MongoDB, because Mongo has a binary format called BSON, and it also has similar extended types. So if you choose to move your data from MongoDB to Oracle, we want to be able to do that without losing any of your information. And the next more interesting reason we did it is for performance. So we've very carefully designed this format to make it very efficient for query and ingestion and retrieval of your data. It's hard to do this topic justice in a short talk, but there's a peer-reviewed paper we published back in 2020 that kind of explains all this in gory details. Because every database vendor is going to present to you and say, hey, we're really fast. And I'm about to do that same thing here. But there's very, specific innovations that we've come up that are the reason why we're able to meet or exceed the performance of these kind of pure play NoSQL databases. But there's a couple things I wanted to point out about it. The first is that when this data is encoded as OSIN, it's just smaller, right? So as data gets bigger, these bar graphs here represent customer documents. One or two of them are public data sets of JSON data. When you encode it as OSIN, it just tends to be smaller than the BSIN or the JSON text. And because of that, it's very simple. There's less data going across the network, and there's less data being stored and read from disk. And the other, kind of more unique advantage we have here is that this format is designed such that it allows us to do efficient random access in the way that it sits on the disk. So let's say that we have a JSON object here representing this movie. If in SQL here I want to select the year of the movie, I can jump directly to that year value without having to look at the name or the genre of this movie. Now, this might not matter for a small document like this in this example, but if you imagine this document getting bigger to like kilobytes or megabytes, it can make a huge difference that if I only want to access the year, I only look at the year. I don't have to scan through the rest of that megabyte JSON document. It can be a huge differentiator. Then the other thing we do is that when you pull this data down to your application, we send it over the network as it sits on disk. We don't spend a lot of CPU cycles on the server converting it to some other format. And then that smaller representation is transmitted over the network. And then when it gets to your Java application, we do exactly the same trick. So if I want to get the year of that movie, we just jump straight to the value. We don't have to convert this to some in-memory hash table or something like that. And so what this format allows us to do is to give you extremely low latency access to that first value that you want to retrieve. And so because of these innovations, even on these pure play NoSQL benchmarks, we're competitive, right? So the kind of gold standard for NoSQL database is called the Yahoo Cloud Service benchmark. And it's really simple. It just measures gets, puts, retrievals, and it measures how many of them you can do per second, and then what the average latency of those operations is. And so even on these pure play NoSQL benchmarks, we can meet or exceed the performance of our competitors. And we do this while maintaining, read committed consistency with durable writes. We don't relax those beneficial properties of persisting your data. Okay, so I'm going to take a break from slides now and show a short demo. So if you log into our cloud, you'll see a screen like this. And so I'm going to click now on this hamburger menu and click on Oracle Database. And so here's the autonomous database I mentioned briefly, the kind of managed version of Oracle Database. And so if I click on Autonomous Database, I can click Create Database. And you basically enter some basic information here, like the name of the database, what flavor do you want? These three databases all kind of have the same functionality, but data warehousing is more for reporting and analytics. Transaction processing and JSON are functionally equivalent to each other. Same performance characteristics, same functionality. JSON is just cheaper if you only want to do this document JSON stuff. You get it at a lower price, and it only lets you store a little bit of other types of data. Then you select a version. Highly recommend selecting 23 here, and especially if you're doing MongoDB compatibility type stuff, because there's a lot of advancements in version 23 versus 19. You pick an initial scale in terms of compute and storage capacity, and you enter administrative password. So here, if you want to do the MongoDB stuff that I'm going to show in a moment, you want to pick one of these two options, because we don't let the MongoDB wire protocol go over the internet. So one thing, if you're just playing around and you're not worried about security, you can pick this option, and you can pick CIDR block and enter 0.0.0.0/0. So this adds network controls, but the network control I'm adding here basically says allow access from any IP. And then that's basically it. So if I clicked create here, it would go, churn away for about a minute, and then this database would be ready to go. But I already created one for this demo. And so after it's created, you'll get something that looks like this. And so for this demo today, um, I'm going to start by issuing some SQL. So if you click on SQL right here, what happens is that this tab right here will pop up. And so what I'm going to do to start out is I'm going to create a table like the one I had in the slides. So here I'm creating a table called movie, and it has a column named data type JSON. And so here it says table created. And now I'm going to insert some movies into this table. So I'm inserting the movie The Shawshank Redemption, which has a title, genre, and gross sales. There's the matrix, and the matrix has a contact, which is my email address. And that's okay. That's the point. They don't all have to have the same attributes. And then there's one for Interstellar. So I'm going to do these inserts. So now, if I select from this table, you can see there's the 4 JSON objects or 3 that I inserted. But I can go further than just dumping them back out. We can actually use what we call the simple dot notation here to project out these attributes like relational columns. So if I run this version, I get a kind of familiar looking relational result where I've got the title in one column, the genre, the gross, and so on. And I also projected out contact, and 2 of the JSON objects didn't have contact, but that's okay. You just get a null if it doesn't exist. And so now at this point, you can do anything, from SQL that you're used to doing. Like, let's say I want to filter these and just select the one where the contact is equal to Josh. So we just get back the matrix. Or I can do any kind of analytics group by queries that I want to do at this point. So here, I'm going to do a group by on the genre attribute, and I'm going to count the number of movies with that genre, and then sum the gross sales. And so here I get 2 rows, one for drama, there was 1, and sci-fi, there was 2. So the point here is that once you're able to project out the attributes from the JSON, you can join it with other types of data or do anything, that you're used to doing, with Oracle SQL. Okay, so that's basically the idea. We have this JSON column. You can store your JSON in that column, and you can access that data with SQL. So break from slides is over, and we're going to do one more section, and then I'll finish it up with a demo. Just to get my slides back here. Okay. So the next section is about JSON collections. This is a new feature in Oracle Database 23. So the reason we added these JSON collections is for better compatibility with MongoDB. MongoDB doesn't support multiple types of data. It doesn't have tables with rows and columns. The only thing MongoDB has is these simple collections of JSON objects. So to be more compatible with NoSQL document stores, we've added a special type of table called a JSON collection table. When you create one of these, it automatically creates a table that only stores JSON documents. You don't specify the column names or types. So in the example here on this slide, it's creating a JSON collection table called movies. And I'm not telling it anything about the columns. And then I immediately am able to insert a JSON object into that collection. The other difference with a normal table that has a JSON type column is that the JSON documents in a collection must have an ID field within the JSON. This ID field serves as like a primary key. This is very similar to MongoDB. If you don't include one of these ID fields in your data, the database will generate one automatically for you. And now the third point about these JSON collections is that unlike normal tables, they're going to be automatically visible to MongoDB and these collection-based APIs. And so I'm going to come back to that in 2 slides. But before that, there's actually 3 different types of collections that we have. There's collection tables, which store the JSON documents as this OSON format. These are like the collections that you would get if you created a collection in MongoDB. They're basically storing the binary encoded format backed by block storage. And there's also, though, we have collection views, which produce a JSON value defined by a SQL query. And so these collection views are typically read only. So here it's creating a view called movies, but it's creating that view based on a SQL query that maps a relational table to a JSON object. So it doesn't actually store the data. It's just kind of like a view of data as JSON. And then finally, we have duality views. Duality views are a very important feature of 23AI. They're like a collection view. They're defined by SQL, but the difference is that now you can read and write to them. So like when you insert a document into a duality view, for example, the data is automatically propagated to inserts on the underlying relational tables. And the same happens for updates and deletes and so on. I'm going to show an example of this in my demo. But people are really excited about this because duality views allow you to store your data relationally. So you get all the benefits of data normalization, removing duplication, efficient storage, but you keep the client-side benefits of all these things that developers like about document storage. And it also allows you, if you have a MongoDB app, you can take data that might be in some other format, like a relational normalized system, right? And you can expose that to your MongoDB apps, and they don't even know that they're not working with a normal collection. Anyway, I'll show more about this shortly. But then finally, we have this MongoDB-compatible layer. We call it the Oracle API for MongoDB that works on top of these collections. So MongoDB doesn't have a concept of tables like Oracle does. It just has these simple collections of JSON-like values. So we've added a compatibility layer that lets you connect these MongoDB tools and language drivers to Oracle database. So you can take an application that was originally written against MongoDB and make it run against Oracle database instead without having to change any of the application code. So given they don't have tables, the next few slides kind of explain how this works. So in this blue box on this slide, it's some Java code that was written to run against MongoDB. And so I'm going to step through and explain what these lines of code mean if you were to instead run them against Oracle database. So Mongo has this concept of a database, and a database groups together collections. It's very similar to Oracle's concept of a schema, which groups together tables. So if you say, I'm going to work with database admin, really what we're saying underneath the covers is that this is going to refer to the schema called admin. If you call this method create collection, underneath the covers, it's going to create a JSON collection table that I just showed a few slides back. If I insert a document into that collection, underneath the cover, it's going to translate it into a SQL insert. And then finally, if I filter the data, so Mongo has this filter expression language. Sometimes it's called like query by example. If I want to filter my data underneath the covers, that filter is going to be translated into a SQL select query. So our basic elevator pitch here is the following. If you're building a microservice or application where you simply want to persist your data, just save your application object, then SQL may not add much value. And it may actually make the application code a bit more verbose. And it can be a barrier to entry for some developers. So collections allow you to very simply get and put your data, write your app. But when you create one of these collections, it's actually creating one of these JSON collection tables that's still accessible using SQL. So the idea here is that you get the best of both worlds. You can have your simpler development model for writing up your app, but the whole time you're doing that, you never lose the ability to use SQL for analytics over that data if you choose to do this. And so I'm going to start another demo of this shortly. But I wanted to talk first about some very exciting things, or things that we find in the development team exciting with the Mongo API. It's no longer just a story about us proving that we can do whatever MongoDB can do. We're actually starting to go beyond what they can do with their own protocol. So connecting a MongoDB app to Oracle, you can do more than you could do if that same app was connected to MongoDB. And so one example of this is the $SQL stage. So this lets you execute SQL directly from a MongoDB aggregation pipeline. So here, I'm connected to a MongoDB shell, and I'm doing db.aggregate, and I'm passing this $SQL stage, and I'm giving it a select query on a normal relational table called department. And it automatically selects those rows from that table and returns them as JSON objects in a form that the Mongo client can understand. It doesn't know that it's getting data from a table. Another example of this is the external stage. MongoDB notoriously does not have external collections. If you want to process data in MongoDB, the data has to be stored inside the database. This is not the case in Oracle database. We have a very sophisticated external table framework, which allows you to query and access data that's stored outside of the database. And so we've added this same functionality to MongoDB connections. So if I have, in this example, I have $external in this pipeline here that accesses a dump file that's stored on GitHub. Right? So the documents from this file stream into this pipeline, and then you can use normal MongoDB aggregation stages on top of it. So I'm going to demo this shortly here. Okay, so slides are done. Let's go continue our demo. So I'm going to go back to this database that we were using here. And I'm going to click on this tool configuration tab. And if I scroll down here, there's a section called MongoDB API. And what it gives me here is a connection string that MongoDB clients can understand. And I'm going to take this connection string and I'm going to give it to MongoDB Compass. So MongoDB Compass is MongoDB's client UI. It allows you to kind of connect manually to the database and interact with it. So I'm going to say, I want a new connection, and I'm going to paste this connection string. And connect. And so now it shows that I'm connected, and if I click on admin, it doesn't show any data. There's nothing here. But in the demo, I had created this table called movies. So if I look at the SQL level, it shows a table called movie. So what's going on here? MongoDB Compass doesn't understand tables, so it can't see them. So let's start over here. I'm gonna drop that table. And now what I'm going to do is I'm going to create one of these JSON collection tables. So now if I go back and I click refresh, we can see it because it's a collection and Compass knows how to deal with that. And it's empty. So I can, insert documents into this table. And so I inserted one movie here. And if I go back to the SQL side, I can still insert, because SQL's fine. It doesn't care if it's a collection or a table. And so now if I run these again, you can see here that I have all 4 movies. So now we've got this collection and MongoDB Compass is happy. But I'm to kind of make this demo more interesting, I'm going to load some more than just 4, small little movies. So I'm opening MongoDB shell now. and I want to load some more data. So what I have here set up, let me show it in a web browser first. I have a dump file of some JSON data. Um, so this is just a text file, and it has a few thousand movies where each movie is like a line in this text file. So I'm going to go to Compass now, see if we can access that using this external stage. And so we see, okay, there's the contents of the file, great. But let's load it now. So I'm going to combine the external stage, and I'm going to pipe those documents to the normal MongoDB out stage. Okay, and so now I'm going to check that the data was loaded. So I will run the count documents function. And we see we have 3,800 movies in this collection. So now if I click find again, you see you've got a whole bunch of data now. And so now I can do any of the normal stuff that I'm used to doing with MongoDB. So if I want to find the matrix, title equals matrix, I get back that movie. And these things can kind of get, uncomfortably complex. So like here, I'm going to filter where the year attribute is greater than 2018. And so I only get back those movies here. But maybe I'm worried that, having to scan all the data for these, movies, on this year value would be too expensive. Maybe I've got a lot of movies. So the other thing I can do is I can, create indexes here. So what I'm going to do is create an index on the year attribute. And so now if I come back here and do an explain plan on this, we can see that it's now using a index to execute this query. There's not enough data here to really tell, but now it's efficiently using the index to pull back just the movies that have a year greater than 2018. But kind of the cool part is that I can go run this same query now from SQL if I want to. All right, so here I'm going to do the same query, and I'm going to select all the movies where year is greater than 2018. They come back. But here's the neat part, right? It's using that same index I just created from the Mongo API. So you can really think of like whether you're coming at the data from SQL or coming at it from the Mongo API, they're just ways of accessing your data. All the same stuff is happening underneath the covers. It all works together. It doesn't matter which way you choose to access your data. Drive this home a bit further. Let's say now I want to do some analytics. I can, use a select query directly over this movie table to group movies by the year and count how many we have. And then if I don't like writing SQL and I don't want to do that, that's okay. You can use a normal MongoDB aggregation pipeline. And so here, I'm using match, group, and sort, but I'm basically doing the same thing that I did from the SQL query. So again, you like these aggregation stages from MongoDB, your app already uses them, you can continue to use them, it's fine. If you think SQL is a more elegant, expressive way to access that data, you have that action, opportunity as well. Okay, almost finished here. So let's go back now to SQL, and I'm going to do some stuff that MongoDB can't do over this data now. So I'm going to do a kind of more complicated analytic query. So here I'm using, window functions, and basically what I'm doing here is I'm for each year computing a percentage that year contributed to the overall revenue. So like here, 2016 attributed to 5% of the total revenue. And so what I'm going to do now is I'm going to take this query and I'm going to create a little report here. So I'm going to click on charts, create a new chart, call it rev by year. And I'll say it's not protected. Paste that query in. and I'm going to say it's a bar chart. I'll say the x-axis is the year, and this is the percent. So I've created, a fairly complex analytical report over this JSON collection using SQL. But notice here, probably because of COVID, there's not much revenue around the year 2020. I'm going to go back to Compass now, and I'm going to find one of these movies from 2020. So here's one, and I'm going to edit this document, and I'm going to modify the gross sales here, if I can. Say that this is I'm going to say, so I'm giving this one movie in 2020, an unrealistic, amount of revenue here. And the reason I'm doing this, if I come back and refresh now, you see a bunch of revenue jump up in 2020. So the point of showing this was you can do these analytic reports, but there's still like very much a live active view of your natively stored JSON collections. Now, one final thing I would like to show is duality views. So let's say now, what if I had some plain old boring relational data? Right? So I'm going to create a table here called theater. And theater is really boring. It just has a name, an address, and a capacity. It's completely flat. If we go back, I'm going to insert 6 theaters into this table. And again, we go back to Compass now. And if I refresh this, it just still only shows movie. Doesn't show anything about theater yet, because it's a table. Compass doesn't know how to deal with that. So what I'm going to do is I'm going to create a duality view over this theater table. It's called JTheater. And so JTheater is just constructing a JSON object for each of these relational columns. Pretty simple, right? It's saying, okay, I know this is relational, but I want you to show it as a JSON object. So here I create this duality view, and it's not really changing any data or doing anything. It's just, defined by SQL. It didn't store any data in doing this. But now if I select it gives me a JSON view of this data here. And if I select from the base table, that you can see the, flat, boring relational data. Okay, so I'm going to focus in on this specific row here, theater 3. Notice that it has a capacity of 300. I'm going to go back now to Compass. If I refresh now, it can see the duality view, JTheater, because it's a collection. And if I look at it, there's my theaters, and I'm going to edit this number 3. So I'm going to edit 3. I'm going to say that the capacity is 999. Okay, so I updated it to 999. And so now I go back to SQL and I select this this theater again. Now the capacity is updated. So that modification from the Mongo API pushed that change down to that underlying theater table. So even though the data is stored relationally, it's not real JSON data, the duality views are able to, trick these Mongo clients into thinking that it's JSON data. And so you can then bring other types of data. You can bring other types of data that you have stored and make it accessible to these MongoDB applications. So you can do more with a MongoDB client, with Oracle database than you can do with actual MongoDB. So the overriding theme here is that, you get more with NoSQL document storage in Oracle database than you will with one of these pure play databases. And you can store your data, you can access it from SQL, you can access it from a Mongo client. It doesn't matter. Your data is your data, and it's all the same underlying architecture underneath. And so this concludes what I wanted to present and demo today. So I appreciate everybody giving me the time today and joining us. Were there any questions about any of this?
There were a couple questions. I answered them in the Q&A, but if there are any more questions, now would be the time, I guess. This was excellent, Josh.
Oh, thanks, Peter. Okay, then. Well, thank you, everybody, for joining us, and have a good rest of your day.